Okay, let's dive in. You hear a lot about AI in healthcare, right? Helping doctors diagnose complex conditions, maybe finding patterns humans miss.
Yeah, it's moving beyond theory. And neurological conditions are a really fascinating area for this. Brain activity patterns hold so many clues.
Absolutely. So today we're doing a deep dive into a specific project using machine learning to detect seizures from EEG data, which, is notoriously hard to monitor constantly.
Right. And our source is this web application they built, which is great because it lets us sort of peek behind the curtain, see the data, the transformations, the model's results.
So our mission here is to really unpack this, understand the data they started with, how they turned brain signals into something a machine can learn from.
Exactly. And then look at the AI model itself, how it was trained. There's
Yeah.
some really interesting nuances there and, what the challenges still are.
Okay, let's start with the data. EEG. Most people have seen those squiggly lines, right? Electrodes on the scalp picking up the brain's electrical buzz.
hmm But raw EEG,
Mm.
it's just a time series, a lot of data points over time. Not ideal for, say, an AI model that's really good at looking at pictures.
Ah, okay, so they need to change its form.
Precisely. And the key step here is transforming it into a spectrogram. You can think of it almost like a visual fingerprint or a heat map of the brain's frequency activity over time.
Heat map. So showing intensity at different frequencies.
Yeah, lower frequencies, higher frequencies, and how strong the signal is at each point in time. And the thing is, seizures often create really distinct patterns on these spectrograms, different colors, different intensities in specific frequency bands.
So you're turning these electrical signals into images where seizure activity might visually jump out.
That's the core idea. You're giving the AI a visual representation that highlights potential seizure markers. It makes the pattern recognition task much more feasible for certain types of models.
And this data, it's from actual patients.
Yes, it's derived from EEG recordings of epilepsy patients. They leverage the CHB MIT Scalp EEG database, which is a really valuable, well-known public resource for this kind of research.
And the source material, the web app, it actually shows these spectrograms.
It does. You can apparently navigate it and see examples side by side, a spectrogram from a time segment with a seizure and one without.
And can you actually see the difference?
Often, yes. You might see like a band of bright color appear in the seizure spectrogram that isn't there or isn't as intense in the non-seizure one.
Yeah.
It's that visual distinction the machine learning model is trained to spot.
Okay, so
It's this bit, by the way, that you see in here. It's very faint on this example, but some of the other examples are better. It's the validation data. The test data. Yeah, it's noisier for whatever reason. Yeah, the validation is better. Someone must have selected. Yeah, so you see those patterns in the spectrogram. So this is where the seizure is happening. So hopefully later on, the convolutional neural net is actually trained on detecting those and potentially even predicting the future.
In the seizure spectrogram that isn't there or isn't as intense in the non-seizure one.
yeah.
It's that visual distinction the machine learning model is trained to spot.
Okay, so you have these images. What's next? Standard procedure.
Pretty much. You split the images into your data sets,
Mhm.
training data to teach the model the patterns,
Right.
validation data to tweak the model during training and make sure it's not just memorizing,
Mm-hmm.
and then the test data. That's the final exam, images the model has never encountered before, to get an honest measure of how well it performs.
Makes sense. Train, validate, then the real test. So what kind of AI model, what brain did they use to learn from these spectrogram images?
They went with a convolutional neural network, a CNN.
Ah, the image recognition specialists.
Exactly. CNNs are kind of the workhorses for image analysis tasks. They're designed to pick out spatial hierarchies of features in pictures, which is perfect for spectrograms.
So the CNN's job is simple. Look at the picture, say seizure or not seizure.
Fundamentally, yes. The model architecture is built for that. It starts with an input layer that accepts the spectrogram images, which have a specific size, height and width in pixels, and color channels.
Okay, takes the picture in, then what?
Then it hits the convolutional layers. Think of these as banks of filters, like little digital magnifying glasses, each designed to look for a specific, simple pattern, maybe an edge, a corner, a certain texture, or a blob of color.
So breaking the image down into basic visual elements first.
Sort of. And they used a couple of these layers, with the filters becoming potentially more complex in later layers, learning to combine simpler features into more elaborate ones, like combining edges to detect shapes relevant to seizures.
Okay, filters find the bits and pieces. What happens after the convolutional layers?
Then you typically have pooling layers. Max pooling is common. It basically downsamples the information. It looks at small regions of the filtered image and just takes the maximum value.
Why do that?
Two main reasons. It reduces the amount of data, making computation faster, and it also builds in a bit of robustness. Like if the key feature shifts slightly in the image, pooling helps the model still recognize it. It focuses on whether a feature is present rather than exactly where.
Okay, so summarize, make it a bit more flexible.
Right. After going through these convolution and pooling stages, the data, which is still kind of in a grid format, gets flattened into one long line of numbers.
Flattened.
Yeah, just rearranged into a single vector. This prepares it for the final layers of the network, the dense layers or fully connected layers.
And these dense layers make the final call.
Pretty much. They take all those high-level features extracted by the earlier layers and learn how to combine them to make the classification. The very last layer usually has, in this case, two outputs, one representing seizure, one non-seizure, and uses something called a softmax function to give probabilities for each.
So it says like 85% chance this is a seizure, 15% chance it's not.
Exactly like that. Okay, so we've got the spectrogram pictures and the CNN model designed to analyze them. How do you actually teach the model? What's the training process look like?
Right, the learning part.
Okay, first step is loading all those images. And crucially, you need to label them. Tell the computer, this batch of images corresponds to seizures, let's call that 1, and this batch is non-seizure, let's call that 0.
Digital flashcards, image and answer.
Precisely. Then you divide them into those training, validation, and test sets we mentioned. Before you feed them to the model, though, some important prep work happens. Normalization is key.
Normalization, what's that?
It's about scaling the pixel values. Images often have pixel values from 0 to 255. Normalization might rescale these to be between 0 and 1.
Why bother?
It just helps the model learn more effectively and stably. Large input values can sometimes cause issues during the complex calculations inside the network. It keeps everything on a similar scale.
Okay, makes the numbers easier for the model to handle.
And those simple 0-1 labels, they often get transformed too into what's called one-hot encoding. So instead of 0, it might become 1, 0, and instead of 1, it might become 0, 1.
Seems more complicated. Why?
It just matches the format of that final softmax output layer we talked about, which outputs probabilities for each class. It's just a technical step to align the labels with the model's output structure.
Got it. So data prepped, labels formatted. Now, the actual training, are there settings you need to fiddle with?
Oh, absolutely. These are the hyperparameters, the knobs you tune before training starts.
Yeah.
They experimented with several key ones, like the batch size, how many images the model sees before updating its internal weights. They found batch size of 64 seemed to work well in some runs.
Okay.
The number of epochs, how many times the model goes through the entire training data set. They mentioned using 100 epochs gave better results in some cases, more cycles to learn.
Right.
And the learning rate, basically, how big a step the model takes when it adjusts itself based on errors. They used a common starting point of 0.001. Too high, it might overshoot. Too low, it learns too slowly.
So finding that Goldilocks zone for learning speed.
Exactly. They also chose a specific algorithm to handle these updates, the atom optimizer, which is very popular and generally effective, and a loss function binary cross entropy, which is standard for this kind of two-class problem. It measures how far off the model's predictions are.
And they tracked accuracy during training too, right?
Yes, accuracy was the main metric they watched.
Yeah.
Interestingly, they also experimented with data augmentation.
What's that? Like creating fake data?
Sort of. It means artificially modifying the training images, rotating them slightly, zooming in, changing brightness. The idea is to show the model more variety, make it more robust.
Did it help here?
Apparently not. In their tests, they found they got better results without augmentation, which is a bit counterintuitive sometimes.
Huh, interesting.
But something that did help was shuffling the data, making sure the model saw the training images in a random order, each epoch. That prevents it from accidentally learning patterns based on the order it sees things.
Okay, so tuning these knobs, shuffling, anything else to help manage the training?
Yes, they use callbacks. These are like little automated helpers. One is model checkpoint. It automatically saves the best version of the model during training, usually based on its performance on the validation set.
Smart. So you don't accidentally keep a worse version if performance dips later.
Exactly. And early stopping. This washes a metric, like validation loss, and if it stops improving for a certain number of epochs, it just stops the training process automatically.
Prevents wasting time and overfitting, right? Where it just memorizes the training data.
Precisely. Prevents it from learning the training data too well, at the expense of generalizing to new data.
Okay, so training's done thanks to these settings and helpers. Now the crucial part. How do you know if the model is actually any good? How do you evaluate it?
Right, evaluation. The headline number is usually accuracy. What percentage of the test images did it classify correctly overall?
And they mention a range there.
Yeah, they observed results anywhere from around 80% up to 95% accuracy on the test set, which really depends on the specific configuration and run.
That's quite a spread.
It is, and it hints at some complexities we'll get to. They also track the loss on the test set again. Lower is better, indicating less error.
Okay, accuracy and loss, standard stuff.
But for medical applications like this, overall accuracy isn't the whole story. Not even close. You absolutely need to look at the confusion matrix.
Okay, break down the confusion matrix for us.
Yeah.
It sounds confusing.
Well, it can be at first, but it's incredibly useful. It's basically a table that shows you a breakdown of the model's predictions versus the actual truth.
So 4 possibilities.
Exactly. You have true positives, TP. The model correctly said seizure when there was a seizure. Good.
Okay.
True negatives, TP. The model correctly said non-seizure when there wasn't one. Also good.
Right.
Then the errors. False positives, MP. The model said seizure, but it was actually a non-seizure segment, sometimes called a false alarm.
Annoying, maybe, but perhaps not critical.
Depends on the context, but generally less critical than the last one.
Sure.
False negatives, FN. This is when the model said non-seizure, but there was an actual seizure happening.
Ah, that's the one. That's the miss you absolutely want to avoid.
That's the critical error in this scenario.
Yeah.
Missing a seizure could mean delayed treatment, serious health consequences. So when evaluating a model like this, you might prioritize minimizing false negatives, even if it means accepting a few more false positives.
That makes total sense. The clinical impact of the error type is paramount. It's not just about the overall score.
Absolutely. You need to understand the trade-offs. Looking at the raw numbers in the confusion matrix tells you exactly how many of each type of correct and incorrect prediction the model made on the test set.
Did they also look at the specific images it got wrong?
Yes, that's another crucial step mentioned. Analyzing misclassified images. Why did the model get this specific seizure spectrogram wrong? Was the seizure pattern unusual? Was the data noisy?
Clues for improvement.
Exactly. It helps you understand the model's weaknesses and guides future work. And finally, there's the training log, which summarizes the whole run the settings used, the performance metrics epoch by epoch. It's the record of the experiment.
Okay, this evaluation discussion sets us up perfectly for, I think, one of the most intriguing findings they reported, the comparison between run 9 and run 10.
Yes, this is fascinating. So they performed multiple training runs, and they specifically compared 2 runs, run 9 and run 10, where they used exactly the same configuration.
Define exactly the same.
Identical data set splits, identical image size, batch size 64 for both, 100 epochs for both, 0.001 learning rate for both, no data augmentation for either, shuffling enabled for both, every hyperparameter, every setting we just discussed, identical.
Okay, so naturally you'd expect the results to be identical, or at least incredibly close.
That's what intuition suggests. But listen to this. Run 9 achieved a test accuracy of 96.00%. Really good.
Wow, okay.
Run 10 with the exact same setup. Test accuracy, 90.00%.
6.5% lower, just like that.
Just like that. And it wasn't just test accuracy. Run 9 had better average training accuracy, better average validation accuracy, lower average training loss, lower average validation loss compared to Run 10, consistently worse performance despite the identical setup.
Hold on, how is that even possible? If the inputs and the rules are the same, shouldn't the output be the same?
This is such a key point about deep learning. The process isn't fully deterministic. There are elements of randomness or stochasticity involved in the training.
Randomness, wait.
Well, a couple of places primarily. One is the initialization of the model's weights, those internal parameters the model learns. Before training starts, these are typically set to small, random values.
So the starting point is slightly different each time.
Yes, tiny differences at the very beginning. Another source is the shuffling. Even though shuffling is enabled, the specific random order in which batches of data are presented to the model can differ slightly from run to run.
So the sequence it learns from isn't exactly the same.
Not precisely the same order, even if the overall data is identical. And these tiny initial differences in weights or the tiny variations in data presentation order,
They can snowball, like a butterfly effect.
that's a perfect analogy.
Right.
Over the course of, say, 100 epochs, with millions of calculations, these minuscule initial variations can lead the model down slightly different paths during learning, resulting in final models with noticeably different performance characteristics.
Wow. Okay. So the huge takeaway here isn't just run 9 was better than run 10. It's that a single run, even if it looks great, might not be representative.
Precisely. It hammers home why you absolutely cannot trust the results of a single training run in machine learning. You have to run experiments multiple times.
Or use techniques like cross-validation.
Yes, techniques like k-fold cross-validation, where you systematically train and test on different chunks of the data multiple times, help give you a much more robust estimate of how well your model is actually likely to perform on unseen data. It averages out some of that randomness.
So this variability, this stochastic nature, is just part of the deal with these complex models.
It is. And understanding it is crucial for doing reliable machine learning research and development. Don't just report your best run. Report the range, the average, the standard deviation across multiple runs.
That's a critical lesson. Okay, so given these promising results, but also understanding this inherent variability in the evaluation needs, what are the big hurdles still ahead for something like this? What are the challenges?
Well, there are quite a few. One is continuing to fine-tune those hyperparameters, the learning rate, batch size, maybe even the model architecture itself. Finding that optimal configuration to squeeze out the best, most reliable performance without overfitting is still part science, part art.
The tuning challenge.
Definitely. Another big one, very common in medical data, is data imbalance.
Wow.
You usually have way more non-seizure data than seizure data.
Right. Seizures are relatively rare events in the grand scheme of brain activity.
Exactly. And if the model sees vastly more non-seizure examples, it might just get really good at predicting non-seizure all the time, achieving high overall accuracy, but performing poorly on the crucial seizure detection task. So strategies to handle imbalance, like oversampling the seizure class, undersampling the non-seizure class, or using specialized loss functions, need exploration. They mentioned looking into augmentation and sampling.
Okay, balancing the scales. What else?
Improving robustness is huge. Will a model trained primarily on data from the CHB-MIT database work well on EEG data recorded using different equipment, maybe in a different hospital with different protocol?
The domain adaptation problem, making
Yeah.
it generalized.
Yes, that's a major challenge for real-world deployment. The model needs to be robust to these variations, and then there are two critical factors for clinical adoption.
Let me guess. Interpretability and speed.
You got it. Interpretability, or explainability. Doctors are unlikely to trust a black box. They need some insight into why the model flagged a segment as a seizure. What features in the spectrogram did it focus on? That's key for building trust and integrating it into clinical workflows.
Understanding the why behind the prediction.
And real-time processing. For patient monitoring, you can't wait minutes for an analysis. The detection needs to happen almost instantly to be truly useful for alerts. Making these complex CNNs run efficiently enough for real-time inference on potentially limited hardware is another engineering challenge.
Right. Accuracy, robustness, interpretability, speed. That's quite a list.
It is. But researchers are actively working on all these fronts, exploring different model architectures, like ResNets perhaps, or even models that handle time series data more directly like LSTMs, might be part of the solution. Adding more layers, trying different pre-processing, it's an ongoing process.
So pulling it all together, this project is a really compelling demonstration, isn't it? Showing the potential of deep learning, using CNNs on spectrograms derived from EEG to help tackle a difficult diagnostic challenge.
Absolutely. It lays groundwork, it shows feasibility, it's a step toward potentially creating a non-invasive, AI-powered assistant for clinicians dealing with conditions like epilepsy.
The ultimate goal being.
A tool that's, highly accurate, reliable across different settings, interpretable enough for clinicians to trust, and fast enough for real-time monitoring. That's the North Star.
And it really highlights the collaborative aspect, too, building on established data sets like CHB-MIT, and then contributing back by sharing their process data on platforms like Zenodo.
Yeah, science at its best. Building on previous work, sharing resources, allowing others to verify and extend the findings, it accelerates progress for everyone.
So for you listening, think about this intersection. AI analyzing something as complex and personal as brain activity. What does it mean for the future of diagnostics?
And consider that gap between a model achieving, say, 90% accuracy in a lab setting versus a tool a doctor relies on for critical patient decisions. What does it take to bridge that gap? It's more than just algorithms. It's about trust, usability, integration, and understanding those critical error types like false negatives.
Definitely a lot to think about. The technology, the application, the human element. This has been a fascinating deep dive into machine learning for seizure detection. Thanks for walking us through it.
My pleasure. Really interesting stuff.
Yeah, let me know if there's any questions. There was also an interesting distinction between run 11, run 12, and 13, I think, had exactly the same settings. Yeah, 12 and 13, exactly the same settings, but yeah, just something really bad happened. Run 12 got the test accuracy of 50%, and 13 with the same settings got a test accuracy of 98%. So yeah. So that's the non-deterministic nature of neural networks, or convolutional neural networks in this case. And then run 14, we actually added a random seed. I think it's a standard practice, and that 42 number, yeah, it's the answer for everything. Is it the number? Answer for everything? Well, we added that setting and got the test accuracy of 100%. So no false alarms, no misses. That means no type 1 or type 2 errors. Also means no false positives and no false negatives, only true results. And that's what the model accuracy training and validation looks like over time, well, it's not time, over epochs. So this is essentially showing the model more and more results, and the model loss is reducing, which is a great sign. All the code, yeah, the podcasters forgot to mention that all the code for the training is available on the page, is available for you to just copy paste it into your Python. The dataset is public, so just you can go and grab that and train your own models on it, and you will be able to revolutionize epilepsy, solve epilepsy. Because if you able to make detection of seizures, next thing you will be able to make prediction, because there would be potentially some features that will be changing before the actual event, clinically relevant, the shaking or the fall happens, or loss of consciousness, whatever happens in that particular patient, you will be able to predict it before it actually happens. And that will be a huge outcome for patients, clinicians, and humanity.